All right, before we get into any of this, I wanted to talk about the quiz. I'm just going to be honest with you. This should have been imminently doable. Okay, so I just want to be honest with you. Like, this is something that that you should have really nailed. Okay, so first of all, I had V. Oops, let me choose a different color. V was equal to 5, negative 12. W was equal to negative 4, 3. Okay. In part A, you were asked for a unit vector in the same direction as V. Well, that's going to be V over the length of V. Yes? Okay, so V is just 5, negative 12. By the way, some of you weren't even treating vectors like they were vectors. You were treating them like they were numbers or something. There was just some kind of funny business going on at times. Okay, so divide this thing. That means divide both coordinates by the length of V. The length of V is the square root of 5 squared, which is 25, plus 12 squared, which is 144. This right here, by the way, is 169, which has a perfect square root, right? What's the square root of 169? 13. This is going to be 5/13, comma, negative 12/13. Okay? In part B, it said compute the length of V plus W. Well, that means you need to find the vector V plus W. You don't just find the length of both and then add those together. The length of V plus W is not, in general, going to be the length of V plus the length of W. Remember, how are V, V, W, so here's V, here's W. Remember, V plus W is this guy right here. And you can see right there that the length of V plus W is not the same as the length of V plus the length of W. You can see that the length of V plus W in general, what's going to be the relationship between that length and the sum of the two lengths of the individual things? Think about it. If I was running along V, then W, would I travel a further distance or a smaller distance than V plus W? Further. Yeah? So this is less than or equal to the length of V plus the length of W. Yeah, that's the so-called triangle inequality. You cannot compute the length of the vector V plus W by just adding together their lengths. That is an incorrect way to do it. What you have to do is compute what V plus W is. Okay, well, what is V plus W? Well, 5 plus negative 1, or 5 plus negative 4 is 1. And negative 12 plus 3 is negative 9. Okay? So the length of V plus W is the square root of 1 plus 81, which is the square root of 82. Okay, that's it. All right, any questions on that? So we have a unit vector in the same direction of V. That was part A. Compute the length of V plus W. That was part B. What about part C? We want a vector in the opposite direction as W of length 6. So vector in the opposite direction as W of length 6. Well, opposite direction of W, that just means negate W, yes? So I could take negative W, and then you say, but I want it to be of length 6. But right now, if I take the negative of W, that's going to have the same length as W, isn't it? So how could I make it length 6? Well, one thing you could do is you could first make it length 1. Yeah? How could I make this thing length 1? Divide by the length of W. That will make it length 1. So if I multiply this by 1 over the length of W, this guy will have length, This guy will have length equal to 1. Yeah? So how do I make it have length 6? Multiply that by what? 6. Okay? And that will increase the magnitude by that factor. Okay? So, and now we're in business. Okay, so this is going to be minus W means it's going to be 4, negative 3, because you just negate both coordinates, times 1 over the length of W. Okay, well, that's the square root of 4 squared, which is 16 plus 9, which, by the way, is 25. And you guys know what the square root of 25 is, right? 5. And then I have to multiply all this by 6. So basically, I have to multiply everything by 6/5. Okay, I have to multiply this vector by 6/5. And what are we going to get? 24/5, comma what? Negative 18/5. Okay. Any questions on that? So to get the opposite, hit it with a minus sign. To get length 6, first make length 1, then scale it by 6. Yeah? I wanted it to be length 70. I would scale it to be 1 and then multiply by 70. Yeah? Any questions on that? Okay. D. Okay, part D. What's up with that? Okay, so part D. 2V minus 1/2 W. This is the one that probably surprised me the most. Thought this one would be just lickety split. Okay, so what was V again? It's on the previous slide, but can someone tell me what was V? 5, negative 12. Okay, and then I'm subtracting 1/2 times the vector W. What is W? Negative 4, 3. The thing that surprised me is a lot of you were getting a number as an answer. I don't even know how that was happening, okay? This is going to be a vector. Taking twice V and then subtracting 1/2 W the result is going to be a vector, yeah? I mean, you may recall that if I have, if this is V and this is W, then V minus W is like right here. So this is V minus W, yeah? It's like the third side of that triangle, if you will. And if I take twice V, it's going to stretch out the one side, and 1/2 W, it's going to stretch out the other side. So, I mean, I don't know. I could try to draw this picture. So twice V gets me to right here. Okay. So that's 2V, and then 1/2 W is right here, right? So that's 1/2 W. Okay, and so if I go 1/2 or twice V minus 1/2 W, it's going to be that vector. So this is 2V minus 1/2 W. I'm just showing you this geometrically so you can see what's happening, yeah? And kind of scale these things appropriately and think about it. But I don't even have to think about that picture. I can just straight up do the computation. If I distribute 2 and I distribute negative 1/2, I get 10, negative 24, okay, oops, plus, well, what's this going to be? Negative 1/2 times negative 4, that's like 2, yeah? And what's the other thing? Second coordinate's going to be negative 3/2, okay? So I'm going to get 10 plus 2 in the first coordinate, which is 12. And in the second coordinate, I'm going to get negative 24 minus 3/2, which is negative 25.5, yeah? Which is like negative 51 over 2 or something. Okay. Finally, letter E. This is asking for the length of the vector V plus W scaled by its length. Well, I didn't mean for this to be computationally hard. That thing that you're computing the length of is a vector that has been scaled by its length. So what kind of a vector is that? It is a unit vector. So if I compute the length of it, guess what I'm going to get? 1. Okay. You could have surmised that without even doing any computation at all. Some of you went through the computation itself. You knew the length of v plus w from part B anyways. You could, and you knew you had to compute v plus w along the way to pull that off. So you could have computed the length and you would have realized, oh man, that's just 1, right? But it had to be, because this is a unit vector. You've scaled the vector by its length, and therefore it's going to have length 1. Yeah? Okay, cool. So that's how this thing went. Hopefully that makes sense. Again, this, right, I mean, I hope that before you start kind of working on the test, that this sort of thing makes really good sense. Because you're not just going to be asked about this, I'm going to ask you about things like involving the dot product and the cross product and planes and stuff, right? So you're going to have a fair amount of comfort level with your vectors. Okay. Any questions? Any questions? Okay, this is just a no holds bar session. What questions do you have? Anything in particular that you feel like, oh man, what's going on here? Any particular questions that you have kind of lingering in the back of your mind? There he goes. That's kind of neat, right? Just making sure these people are hearing me. Okay, yes.
The remainder with the Taylor polynomials, when does that matter?
The remainder with Taylor polynomials. Well, it matters in a machine because if you ask for a certain degree of accuracy, you want to be sure that you're giving a certain degree of accuracy. So that's why the remainders end up being important. You want to know how many terms do I have to take before I know that I'm within 17 decimal places of the true answer. Yeah. And so that's going to require having that remainder term, which is basically measuring the amount of error between a power series and the function that it's supposed to be approximating. Yeah. That makes sense. I mean, that's sort of the practical utility of it, right? So yeah. The questions. Yeah, Kira. Yeah, so right, so the question is, just to let the people know online, how much of it's going to cover 10.1, which is the conic sections part, hyperbolas, parabolas, and ellipses. You definitely want to know the equations of those things, okay? And you want to know what those things represent. So remember, you had, for the parabola, you had certain things that were labeled like, you had that directed distance P from the vertex to like the directrix, remember that? Or it was like the directed distance from the vertex to the focus, okay? And so that number P happened to be part of the parabola formula. You need to know the general equation for the ellipse and the general equation for the hyperbola. So those things will be on there for sure. Okay. Yeah.
We also need to know the parametric equations for the ellipse and hyperbola.
Yes, right. So the parametric equation for ellipse, hyperbola. Well, I'm not sure that we spent much time on the parametrization of the hyperbola. That would involve secant and tangent, though. But for the ellipses, for sure, that involves sine and cosine. Yeah, we did that at some point also. Yeah, we parametrized those completely. Yeah, David. Yeah, you should. I mean, you should know, right? So you should know how to compute arc length and surface area based on those parametric equations. So like just know the formula for arc length, and like the surface area situation is the one where you have a rotated curve or something, yeah. So yeah, I would at least have those in your mind, yeah. There was a question here. Will the test go all the way back to 9.7 or 9.8? It will involve stuff from the end of chapter 9 on power series. So I will ask you a question about power series or two, and it will have to do with it will have something to do with some of those standard ones that you know, like the geometric. And remember, there was like 5 kind of core Maclaurin series. There was the one for sine, the one for cosine, the one for the exponential, the one for the logarithm, and then there was the one for the geometric. Those 5 seem to be kind of the bedrock of everything else that goes on. So I would definitely know those. I would know what their radius and interval of convergence is. And there will be a couple of questions that kind of delve into the details of that. There was another question somewhere. Other questions? Kira. What? Okay, so let's see. Is there anything that you can relax on? Well, you know, you can just kick back and relax when things start to get kind of, you know, a little bit crispy in the middle of the test, and think about, you know, spring days and kind of being home over vacation. Let me see. So, hang on a second. Oh man, are you serious? It's gonna make me log back in again. All right. See, I'm gonna look through the sections here with you guys. Just gonna play a movie? No. It's kind of weird. I don't remember it looking like that. Oh, wow. That is beastly. Okay, so I actually just want to look through the table of contents. Okay, so in chapter 9, 9.7 and 9.8, again, we came up with formulas for the basic Maclaurin series, but we mainly used those in the last 2 sections. So representation of functions by power series and Taylor and Maclaurin series, the last 2 sections are going to be the ones with the emphasis. Chapter 10, conics, plane curves and parametric equations in calculus, polar coordinates and polar graphs. I mean, I don't know that I would necessarily like memorize like every type of polar graph or something, you know, like the, you know, lemniscates or something like that, right? But I would be familiar with things like how would I go about sketching, you know, if someone hands me like a basic polar equation, how would I go about sketching that? You know, I might familiarize myself with something like R equal to a number times cosine of theta or sine of theta. You know that that's going to be a circle of some kind. And then there's also the cardioid forms. Remember those? Yeah. So it was like A plus B sine of theta, or some R is equal to A plus B sine of theta. I would familiarize yourselves with that. Area and arc length and polar coordinates. I would say that I would concern myself more with, well, Well, I mean, that was just an extension of some of the things we did in parametric equations, right? We just had a nice formula for that in that particular case. In chapter 11, I said I wasn't going to cover anything that was in 6 or 7 yet, only the first 5 sections. Vectors, space, vectors, dot product, cross product, lines, and planes. But again, I would know the basics of sketching a polar equation, but I wouldn't go like memorize that entire page that I showed you at some point. Yes, Carrie, did you have a specific question? Yeah. Yeah. Okay. Other questions? What else? What else? So like, for instance, I wouldn't expect you to like reproduce the parametrization of the cycloid. Yeah? I mean, that's tricky. We had to do a fair amount of work to kind of figure out what to do with that, correct? In fact, I think I did a whole lecture on that topic, right? That was the one where I was gone that one Friday or Thursday or something, and I kind of uploaded that lecture. Parametrizing the cycloid is not an easy task, but we did it. But I would expect you to be able to parametrize some basic things like circles and ellipses, lines. Those would be things that I would expect you to be able to parametrize. Do you guys know? Okay, so watch this. How would you parametrize? Let me see. Let me kind of go to the whiteboard here again. Okay. How would you parametrize a line? Okay, so I don't know. So like here's a line, y equal to mx plus b. Okay, how would you parametrize this line? So here's x and here's y, the x and the y axis. How would you parametrize that line? How about if you just let x be t? And what would y be? mt plus b. Right? Anytime you have an equation of any kind, that's what the parametrization is going to be. Like if this curve right here is given by y equal to some function of x, yeah? You would parametrize it by saying x is t and y is what? F of t, okay? Now there might be some specific range of t that you want to focus on, correct? Like for instance, on this line, I might not want to get every single point on the line and let t be every single possible number. But the basic parametrization itself is typically fairly straightforward, okay? So for instance, I don't know, suppose that this is the point, oh boy, suppose this is the point A, B, and this is the point C, D, capital letters, and I wanted to only go from AB. I only wanted to go, I don't want you to think of this as a vector. I want you to think of the orientation of this curve being in the direction where I start at this point and end at this point. Then the way I could pull that off is actually fairly easy. All I have to do is just let t be in the appropriate range that I move from the one point to the other. So what range would t run through? Or sorry, what would be the domain of t that would make this happen? Remember, what's t equal to? X. So what would t run between in order to take me from the point AB to the point CD? Yeah, that's it. Make sense? And by the way, since AB is actually a point on this line, you actually know what B is. B is going to be MA plus little b, right? It's what I would get if I plugged in x equal to a into the equation of the line. What about D? What's D really equal to? MC plus b. I'm just plugging it into the equation of the line, yes? I'm plugging the x value into the equation of the line. So even though I've written A, B, and C, D, I actually know that B is given as a function of the first coordinate, yeah? Or on this equation of the line. Okay, so a lot of the parametrization stuff, I mean, the key is to not outsmart yourself and think, oh man, I have to do something like super complicated. There are a few curves that we have already handled with like sines and cosines, things that aren't functions. But if the thing is a function, it's usually fairly straightforward to parametrize the thing. Okay. All right, other questions? What was the point of parametrizing again? Like, is that just some invention of some mathematician to torture people for all time? The answer is no. Why did we parametrize curves? What was the purpose of that? Yeah. Yeah, that's right. Daniel's saying it too. You guys were both saying, isn't the purpose to make functions of non-functions? Yes. The point is, like a circle is not a function of x. If I look at a circle in the xy plane, it's not a function of x because for a single input, I get multiple outputs at some points on the circle, yeah? Okay, so for instance, if I had the unit circle, the input x produces two outputs, namely 1 and -1, yeah? That's not good. That's not a function. A function by definition means one input produces one output. That's it. You can't have spontaneous generation. You ever learn about that in grade school? Back in the day, like during bubonic plague or whatnot? Like they thought that if I like left a bunch of dirty rags in the corner that rats would appear, right? Or that stuff would just materialize out of nowhere. And you know, Louis Pasteur eventually said, no, life begets life, right? I mean, life doesn't just come from non-life, from a bunch of dirty rags, you idiots. Yes, that's not how this works. He actually was able to call people idiots because he was really, really smart. So compared to Louis Pasteur, we're all kind of dumb. But anyways, a function is like that. You can't spontaneously generate multiple outcomes from outputs from one input. And so what you do is you say, all right, I'm going to introduce another variable that will be my input, t. And the output is not going to be one number anymore, but an ordered pair of numbers, x comma y, yes? So the input is the parameter, the output is x comma y. And then for each input, you have one output now, yeah? So you make a function from a non-function. It was not a function of x before, but now it's a function of this new variable t, all right? So yeah, that's good. By the way, if you wanted an afternoon, right, Kira was talking about wanting to be able to relax. Well, here's something that if during your free time you can look up. Look up spontaneous human combustion. That's a fun thing. I actually did a project on that one time. It was fairly awesome. You ever heard about that? It's pretty weird. And I think it might actually be legitimate. You know, you can find out for yourself, but I'm sure you guys have plenty of time to go waste on the internet about stuff like that. Spontaneous human combustion is literally human beings bursting into flame spontaneously, which apparently happens sometimes, okay? Sort of weird. And some kind of, there's speculation that has something to do with some kind of nuclear reaction that's taking place within the human body or something, but It's weird. It's weird stuff, but it's interesting to read about. Sorry. Other questions? Yeah, that's right. Spontaneous human combustion. Here's another one you can go look up. Look up the Philadelphia experiment. You ever heard about that? No, I don't know what that one is, but the Philadelphia experiment, one of my favorites. Yeah, Daniel knows about it. Philadelphia experiment has to do with Nikola Tesla. There's a fair amount of speculation that Nikola Tesla figured out how to kind of harness electromagnetic fields in such a way that the empty space of atoms was kind of exposed and could make things invisible. And the problem is when he did it, there's a lot of speculation. Again, all of this is kind of speculative, and it seems like it might have been classified at some point. Lots of stuff started going wrong. like once you did this, once you kind of disturbed sort of the atomic structure by exposing that empty space, and you kind of turned off the fields, it seems like that would just start happening like at other times, like when people were just walking around, for instance. Yeah. So, I mean, I think that there might be some mythical elements sprinkled in here, but I think there's probably some legitimacy in there as well. But Tesla was a very interesting guy. There's a lot of speculation that he was actually murdered by the U.S. government, actually. So that might be a conspiracy theory. I'm not sure. Okay. He defected from Russia, but so other questions? Yeah.
Yeah, so beyond the section in chapter 11 with vectors, how far do we need to go in conics?
Beyond the section in which
Like beyond 11.3, then through 4 and 5, like how much?
well, I just lines and planes is what I'm going to expect you to know how to do. Stuff with lines and planes. Conics weren't until conics. You mean quadric surfaces? Quadric surfaces are in 11.6. Conic sections, I definitely do think you should know. That was back in chapter 10. That was the first section of chapter 10. That was like hyperbolas, parabolas, and ellipses. Okay. But I'm not going to expect you to do anything on there with quadrics. We just did that. All right. Other questions?
Yeah, that one. That's what I'm talking about. So I guess it was at Stanford. They had some psychological experiment where basically in the basement of some building in like Stanford or something, they made a prison, and when people came in, they randomly assigned half of them to be, prison guards and half of them to be prisoners in this simulation. And they were going to have them in there for 3 months and see what it did. But after about 2 weeks, they had to shut the whole thing down because the people who were being the guards were taking it way too seriously and abusing the people who were prisoners.
Oh, man.
And it was just really messed up.
Well,
They came out and discredited it because they were encouraging that.
oh, I see.
So
Huh.
It's discredited, but
Michael's telling us a story about another experiment that you need to look up, but called the Stanford basement prison experiment or something. So, yeah. All right. All right, are we good? What other questions do you have? Yeah, I don't know what's going on with Tesla. There's something weird there, but he's also one of the main characters in a movie called The Prestige. That's definitely a fictional movie.
Is that the one about the magicians?
Yes.
Oh, that's so good.
Yes, it's a very good movie, but he's one of the main characters in that kind of historical fiction, but he did do weird stuff like that. He was a very interesting guy. If you ever want to read an interesting biography, read that one. There was a huge feud between he and Edison. So one was trying to promote alternating current, the other direct current. Tesla wanted a wireless electrical delivery. So he was doing it with like lightning bolts. And Edison kind of went on a propaganda war to like make people afraid of these bolts that he would like shoot out across the sky and things like that. And so Edison ended up winning. But then ultimately Tesla ended up winning because we use his system on the power grid now, not Edison's. Edison's required giant generators like all over the place. Like everybody basically had to have their own generator. Does that make sense? So Tesla won eventually, but he was defeated in the propaganda war.
It was a giant AC/DC war.
Yeah, that's right. It was AC/DC. Yeah, it's one of the most fascinating biographies you'll ever read, Nikola Tesla. All right. That's it. That's all I have.